in the vast, star-studded expanse of the universe, where galaxies spin gracefully and cosmic dust weaves through the void. There lurks a force so powerful and mysterious that it defies our deepest understanding of the cosmos. These are not the gentle giants of science fiction, but real entities, black holes, often depicted as the dark, insatiable monsters of space. Black holes are not just intriguing anomalies, but pivotal players in the cosmic drama. Their influence extends beyond their immediate vicinity, shaping galaxies, governing the growth of stars, and weaving the very fabric of the universe. Imagine a region of space where gravity is so intense that not even light can escape. This boundary, known as the event horizon, marks the point of no return. Once crossed, all paths lead inward toward a singularity, a point where the laws of physics as we know them break down. Yet, within this darkness lies a complexity that challenges our understanding of reality itself. Black holes are not mere voids, but rather enigmatic entities that could hold the key to unlocking the universe's most profound secrets, from the heart of galaxies to the edge of the observable universe. Black holes are deeply intertwined with cosmic evolution. They are thought to be central to the formation of galaxies, influencing the structure and fate of entire star systems. Their gravitational pull can bend light, distort space, and create phenomena that challenge our most fundamental theories of physics. As we continue to explore these cosmic beasts, we confront questions that reach to the very edge of human knowledge. What happens at the event horizon? How do they shape the evolution of galaxies? What can they tell us about the nature of space and time? In this journey through the universe's dark heart, we will unravel the mysteries of black holes, the dark monsters shaping our cosmos. We will explore their formation, their role in cosmic evolution, and the cutting-edge science that aims to reveal their hidden truths. As we delve into their depths, we find ourselves not just investigating distant, elusive objects, but engaging with the very foundations of reality. The study of black holes is not merely about peering into the darkness, but about illuminating the grand tapestry of the universe and our place within it. Birth of a cosmic monster, how black holes form. Black holes are born in the most violent and dramatic events the universe has to offer, the death of massive stars. To understand how black holes form, we must first delve into the life cycle of stars themselves. Stars, including our Sun, are giant nuclear furnaces, burning hydrogen and other elements in a process called nuclear fusion. This process creates a delicate balance. The immense heat and pressure from fusion generate an outward force, counteracting the inward pull of gravity. For stars like our Sun, this balance can last billions of years, but for much larger stars, often those with more than 20 times the mass of the Sun, this equilibrium is fleeting and will inevitably end in spectacular fashion. As massive stars burn through their nuclear fuel, they eventually run out of hydrogen in their cores. With no hydrogen to fuse, the star begins fusing heavier elements, such as helium, carbon, and oxygen, in rapid succession. This process continues until the core is primarily composed of iron. Here's where the trouble begins. Iron is a dead end for fusion. Fusing iron doesn't produce energy like lighter elements do. Instead, it consumes energy. As the star accumulates more and more iron in its core, it can no longer sustain the outward pressure needed to resist gravity. When the core can no longer support itself, the star undergoes what is known as a supernova explosion. The star's outer layers are violently ejected into space, creating a brilliant display that can briefly outshine entire galaxies. Meanwhile, the core collapses under the immense gravitational force. The star, once a luminous beacon in the sky, is reduced to a dense, compact object. If the original star was massive enough, this collapsed core will become a black hole. But what exactly happens during this collapse? As the core shrinks, the force of gravity grows stronger and stronger, compressing the matter in the core to densities that defy comprehension. Once the core is reduced to a certain critical radius, known as the Schwarzschild radius, it becomes a black hole. The Schwarzschild radius marks the point at which the escape velocity, the speed required to escape the gravitational pull of the object, exceeds the speed of light. Since nothing can travel faster than light, not even light itself can escape, rendering the black hole invisible to outside observers. One of the most fascinating aspects of black holes is the nature of their singularities. A singularity is a point of infinite density, where the laws of physics, as we currently understand them, break down. This means that within a black hole, our understanding of space and time ceases to function in any familiar way. It's a realm where the concepts of time, space, and even causality become warped. The formation of the singularity is a direct result of the immense gravitational forces involved in the collapse of a massive star. The mass of the black hole depends on the mass of the original star. Most black holes that form from dying stars are classified as stellar mass black holes, with masses ranging from about 3 times the mass of the Sun to several dozen times its mass. These are the most common type of black holes and are scattered throughout the universe. However, not all black holes are created equal. There are other, more exotic processes through which black holes can form. One of the more intriguing types of black holes is the primordial black hole. These black holes are thought to have formed in the very early universe, shortly after the Big Bang. At that time, the universe was incredibly hot and dense. and small fluctuations in density could have caused pockets of matter to collapse into black holes, unlike stellar mass black holes, which are formed from stars. Primordial black holes would have been formed directly from the chaotic conditions of the early universe. Though they remain hypothetical, primordial black holes are an exciting area of research, as they could potentially account for some of the universe's missing dark matter. Supermassive black holes, the largest type of black hole, are found at the centers of galaxies, including our own Milky Way. While it's unclear how these giants form, one possibility is that they grow by accreting matter over time. Another theory is that they formed through the merging of smaller black holes or the collapse of massive gas clouds in the early universe. Understanding the formation of black holes requires us to grapple with some of the most fundamental questions in physics. At its core, the process is a battle between two opposing forces: the inward pull of gravity and the outward pressure generated by nuclear fusion. In the case of a black hole, gravity wins decisively. As the core of a massive star collapses, the matter within it is compressed to extreme densities, and the star's remaining mass is funneled into a single point, the singularity. This process defies our intuitive understanding of the universe, and yet it's a natural consequence of the laws of physics as we know them. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners that indiscriminately devour everything in their vicinity. Their gravitational influence, while incredibly strong, is limited to a region around them. If our sun were somehow replaced by a black hole of the same mass, the orbits of the planets in our solar system would remain unaffected. The Earth and other planets would continue to orbit the black hole, just as they currently orbit the Sun, although life as we know it would, of course, be impossible without the Sun's light. The concept of a black hole was first predicted by the theory of general relativity, which was formulated by Albert Einstein in 1915. General relativity describes how massive objects like stars and planets warp the fabric of spacetime, and black holes represent the most extreme example of this phenomenon. In the years following Einstein's theory, scientists began to realize that under certain conditions, the equations of general relativity predicted the formation of black holes. One of the first scientists to recognize this was Carl Schwarzschild, who solved Einstein's equations to describe the geometry of space around a non-rotating black hole. For decades, black holes remained a theoretical curiosity. Many scientists doubted that they could actually exist in the real universe. It wasn't until the second half of the 20th century, with the advent of new observational techniques, that we began to find evidence for their existence. One of the key breakthroughs came in the 1960s, when astronomers discovered objects known as quasars, which are extremely bright sources of light located in distant galaxies. It was soon realized that quasars are powered by supermassive black holes at the centers of galaxies, which accrete material and emit enormous amounts of energy in the process. Another major advance came with the discovery of X-ray binaries, which are systems consisting of a star orbiting a compact object, either a neutron star or a black hole. By studying the motion of the star and the X-rays emitted by the system, astronomers were able to infer the presence of black holes in these systems. One of the most famous X-ray binaries is Cygnus X1, which was discovered in the 1960s and remains one of the best known examples of a stellar mass black hole. In recent years, the detection of gravitational waves has provided even more compelling evidence for the existence of black holes. Gravitational waves are ripples in the fabric of space-time that are produced by the acceleration of massive objects, such as the merger of two black holes. The first direct detection of gravitational waves came in 2015, when the LIGO Observatory recorded the signal of two black holes merging. This groundbreaking discovery opened up a new way of studying the universe and confirmed many of the predictions of general relativity. As our understanding of black holes continues to grow, so too does our sense of wonder about these cosmic monsters. The formation of a black hole is a profound event, one that challenges our understanding of the universe and pushes the limits of physics. From the collapse of massive stars to the mysterious processes that may have created primordial black holes in the early universe, the birth of a black hole is a story of extremes, extreme gravity, extreme density, and extreme mystery. While we have made incredible strides in understanding how black holes form, many questions remain. How do supermassive black holes, which are found at the centers of galaxies, grow to such enormous sizes? Do primordial black holes, if they exist, contribute to the universe's dark matter? And what role do black holes play in the evolution of galaxies and the universe as a whole? As we continue to observe black holes with ever more sophisticated instruments, from gravitational wave detectors to high-resolution telescopes, we are likely to uncover new insights into these enigmatic objects. But for now, the birth of a black hole remains one of the most awe-inspiring events in the cosmos, a moment when the fabric of space and time itself is stretched to its limits, and a new cosmic monster is born. The anatomy of a black hole. What lies inside? Black holes, often shrouded in mystery, are more than just dark voids lurking in the cosmos. Their structure is one of the most intriguing subjects in modern astrophysics, offering a window into the extremes of gravity and spacetime. At the heart of every black hole lies its most enigmatic feature, the singularity, a point where density becomes infinite and the known laws of physics break down. Surrounding the singularity is the event horizon, the boundary beyond which nothing can escape the black hole's gravitational grip. To truly understand a black hole's anatomy, we must start with the event horizon. This is the point of no return around a black hole, defined as the boundary where the escape velocity equals the speed of light. For any object or light ray that crosses this boundary, there is no possibility of escape. the event horizon is not a physical surface, but rather a mathematical boundary that marks the limits of our observational capacity. Once something crosses this boundary, it inexorably moves toward the singularity, never to return. The event horizon's size depends on the mass of the black hole. For a stellar mass black hole, which might be several times the mass of the Sun, the event horizon could be only a few tens of kilometers across. For supermassive black holes, like those found at the centers of galaxies, the event horizon can span billions of kilometers. This immense size highlights the extraordinary gravitational pull exerted by these cosmic giants. Inside the event horizon, the concept of time and space becomes profoundly warped. According to Einstein's theory of general relativity, the intense gravity of a black hole bends space-time to such an extent that it creates a funnel-like geometry. This warping effect means that as one approaches the singularity, the paths of particles and light are increasingly distorted. The closer you get to the singularity, the stronger the gravitational pull, leading to a phenomenon known as spaghettification. This term describes how objects stretching toward the singularity would be stretched thin like spaghetti due to the intense tidal forces. The singularity itself remains one of the greatest mysteries in astrophysics. It is theorized to be a point of infinite density, where all the mass of the black hole is concentrated. The core principles of general relativity suggest that the laws of physics as we know them break down at the singularity, creating a realm where the very fabric of space-time becomes infinitely curved. This presents a significant challenge because our current theories, general relativity, and quantum mechanics are unable to fully describe the conditions at the singularity. This discrepancy indicates the need for a theory of quantum gravity, which would unify general relativity with quantum mechanics and offer a complete description of black holes. Another crucial feature of black holes is their event horizon's spin and charge, which can significantly influence their properties. When black holes spin, they are described by the Kerr solution to Einstein's equations, which accounts for the rotational effects. A spinning black hole drags space-time around with it in a phenomenon known as frame dragging. This effect can lead to the formation of an ergosphere, a region outside the event horizon where objects cannot remain stationary relative to distant stars. The presence of the ergosphere enables the extraction of rotational energy from the black hole, a process theorized by physicist Roger Penrose and known as the Penrose process. This theoretical mechanism suggests that energy can be extracted from a rotating black hole, potentially powering some of the most energetic phenomena observed in the universe. Charged black holes, described by the Reissner-Nordstrom solution, possess an electric charge and create an additional structure called the charged black hole's outer horizon. This charge influences the geometry of the event horizon and introduces the concept of the Cauchy horizon, a boundary within the event horizon where predictability breaks down. However, charged black holes are theoretical constructs, as no evidence of such black holes has yet been observed. Exploring the structure of black holes also brings us to black hole thermodynamics, an area of research that combines principles of quantum mechanics with general relativity. According to Stephen Hawking's groundbreaking work in the 1970s, black holes are not completely black, but emit radiation due to quantum effects near the event horizon, now known as Hawking radiation. This discovery implies that black holes can slowly lose mass over time and eventually evaporate, a process that challenges the idea of black holes as permanent cosmic objects. Hawking's theory led to the development of black hole thermodynamics, a set of laws that resemble the laws of classical thermodynamics, but apply to black holes. The first law of black hole thermodynamics relates changes in mass to changes in the area of the event horizon and other thermodynamic quantities. The second law states that the area of the event horizon of a black hole can never decrease, analogous to the entropy in classical thermodynamics. The third law posits that the temperature of a black hole approaches absolute zero as its mass approaches zero, though this remains a topic of debate. Despite these theoretical advancements, the practical study of black holes remains challenging due to their inherent nature. Observing the event horizon directly is impossible, as light and other forms of radiation cannot escape its gravitational pull. Instead, scientists rely on indirect methods to study black holes, such as observing the effects of their gravity on nearby stars and gas. For example, the observation of high-energy X-rays from accretion disks surrounding black holes provides crucial information about their properties. Additionally, the detection of gravitational waves from merging black holes has opened a new observational window, allowing scientists to probe the properties of black holes in ways previously unimaginable. The study of black holes is not only a quest to understand these cosmic giants, but also a journey to uncover the fundamental nature of reality as we continue to explore the depths of black holes. We seek answers to some of the most profound questions in physics. What lies at the heart of a black hole? How do black holes influence the formation and evolution of galaxies? Can we reconcile the strange world of black holes with the principles of quantum mechanics and general relativity? As our understanding of black holes advances, we may uncover new insights into the fabric of space-time itself. The search for a unified theory of quantum gravity, which would describe the extreme conditions of black holes, represents one of the most significant challenges in modern science. Until then, black holes remain enigmatic, awe-inspiring objects that continue to push the boundaries of our knowledge and inspire our imagination. Supermassive black holes, the giants at the hearts of galaxies. Among the most extraordinary and enigmatic features of the universe are supermassive black holes. These colossal objects, found at the centers of most galaxies, including our own Milky Way, possess masses ranging from millions to billions of times that of the Sun. Their existence raises profound questions about the formation and evolution of galaxies and the universe itself. Supermassive black holes are distinguished not only by their immense size, but also by their gravitational influence. Their presence at the centers of galaxies is more than a mere curiosity. It plays a crucial role in shaping the structure and dynamics of their host galaxies. The exact mechanisms behind the formation and growth of these giants remain an active area of research, and several theories have been proposed. One prevailing theory suggests that supermassive black holes formed from the collapse of massive clouds of gas in the early universe. In the early stages of galaxy formation, these clouds of primordial gas could have cooled and collapsed under their own gravity, creating the seeds for supermassive black holes. Over time, these black holes would have grown by accreting matter from their surroundings, including gas, dust, and even merging with other black holes. This accretion process is thought to be responsible for the immense size of these black holes. Another theory proposes that supermassive black holes might have formed from the merging of smaller black holes, or from the remnants of the first stars, as galaxies formed and merged throughout cosmic history. Their central black holes could have combined to create supermassive entities. This process of hierarchical merging could explain the extreme sizes observed in some of the most massive black holes in the universe. The growth of supermassive black holes is closely tied to the process of accretion. Accretion occurs when matter falls into the black hole and forms an accretion disk around it. The material in the accretion disk is heated to extremely high temperatures due to friction and gravitational forces, emitting tremendous amounts of energy in the form of X-rays and other radiation. This radiation can outshine the entire galaxy and is responsible for some of the most energetic phenomena observed in the universe, such as quasars and active galactic nuclei. Quasars are incredibly luminous objects powered by supermassive black holes. They are characterized by their intense emission across the electromagnetic spectrum, including visible, ultraviolet, and X-ray light. Quasars are believed to represent a phase in the life of a supermassive black hole, when it is actively secreting large amounts of matter. The energy released during this phase can influence the surrounding galaxy, driving powerful winds and outflows that can impact star formation and the overall evolution of the galaxy. Active galactic nuclei are a broader category of galactic centers that exhibit significant activity due to the presence of a supermassive black hole. AGNs can vary in luminosity and emission characteristics, depending on factors such as the rate of accretion and the orientation of the accretion disk relative to our line of sight. The study of AGNs provides valuable insights into the processes occurring near supermassive black holes and their effects on their host galaxies. The influence of supermassive black holes extends beyond their immediate surroundings. They play a significant role in the evolution of galaxies through a process known as feedback. The intense radiation and energetic outflows from a supermassive black hole can heat up and expel gas from the galaxy, affecting star formation and the growth of the galaxy itself. This feedback mechanism can regulate the rate of star formation and the overall growth of the galaxy, highlighting the interconnectedness of black holes and their host galaxies. Observational evidence for supermassive black holes comes from various sources. One of the most compelling pieces of evidence is the observation of the orbits of stars and gas near the centers of galaxies. By studying the motion of these objects, astronomers can infer the presence of a supermassive black hole and estimate its mass. For example, the motion of stars in the vicinity of Sagittarius A*, the supermassive black hole at the center of the Milky Way, has been used to estimate its mass at approximately 4.3 million times that of the Sun. Another key piece of evidence is the detection of gravitational waves from the merging of supermassive black holes. The merger of two supermassive black holes can produce gravitational waves that ripple through spacetime, providing valuable information about the properties of these objects and their interactions. Observations of gravitational waves from such events have opened a new window into the study of supermassive black holes and their role in the universe. The study of supermassive black holes also involves understanding their growth and evolution over cosmic time. By observing distant galaxies and their central black holes, astronomers can trace the history of black hole growth and its impacts on galaxy evolution. These observations reveal that supermassive black holes were already in place when the universe was only a few 100 million years old, suggesting that they grew rapidly in the early stages of cosmic history. Despite significant progress in understanding supermassive black holes, many questions remain. How did the first supermassive black holes form and grow? What is the relationship between black hole growth and galaxy evolution? How do feedback processes influence the development of galaxies and their central black holes? Future observations and research will continue to address these questions and provide deeper insights into the nature of supermassive black holes. Advances in observational technology, such as the development of next-generation telescopes and gravitational wave detectors, will enhance our ability to study these cosmic giants and their role in shaping the universe. Supermassive black holes are not only fascinating objects in their own right, but also key players in the cosmic drama of galaxy formation and evolution. Their immense gravitational influence, combined with their role in regulating star formation and galaxy growth, makes them integral to our understanding of the universe. As we continue to explore the mysteries of supermassive black holes, we uncover new aspects of the cosmos and gain a greater appreciation for the complex and interconnected nature of the universe. Black holes and galaxy evolution, a cosmic connection. The interplay between black holes and galaxy evolution is one of the most profound and complex relationships in astrophysics. Supermassive black holes, located at the centers of galaxies, are not merely passive occupants, but active participants in the cosmic dance of galactic formation and growth. Their influence extends beyond their immediate vicinity, shaping the structure, dynamics, and evolution of their host galaxies in significant ways. To understand the connection between black holes and galaxy evolution, we first need to explore how galaxies themselves form and develop. Galaxies are vast collections of stars, gas, dust, and dark matter, bound together by gravity. They come in various shapes and sizes, from the spirals and ellipticals we commonly observe to the more irregular forms seen in the early universe. The formation of galaxies is thought to be a process that began shortly after the Big Bang, as tiny density fluctuations in the primordial gas led to the collapse of matter and the creation of the first stars and galaxies. The presence of supermassive black holes at the centers of these galaxies is intricately linked to their evolution. The current theory posits that as galaxies form and grow, their central black holes also evolve. The growth of supermassive black holes is often driven by the accretion of matter from their surroundings. This process involves the accumulation of gas and dust into an accretion disk around the black hole, which heats up due to friction and gravitational forces, emitting intense radiation. This accretion process can significantly impact the host galaxy, influencing its structure and star formation activity. One of the key ways supermassive black holes affect their host galaxies is through feedback mechanisms. As the black hole accretes material, the energy released can produce powerful jets and winds that flow outwards from the galactic center. These outflows can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. This process can regulate the rate of star formation within the galaxy, influencing its overall growth and evolution. In essence, the supermassive black hole acts as a cosmic regulator, balancing the rate of star formation and the growth of the galaxy. The relationship between black holes and galaxy evolution is also reflected in the mass correlation observed between black holes and their host galaxies. Studies have shown a tight correlation between the mass of a galaxy's central black hole and various properties of the galaxy, such as its bulge mass and stellar velocity dispersion. This relationship suggests that the growth of supermassive black holes and their host galaxies are interconnected. One possible explanation for this correlation is that the processes driving the growth of the black hole also influenced the overall development of the galaxy, and vice versa. Observations of distant galaxies and their central black holes provide valuable insights into the early stages of galaxy evolution. By studying these systems, astronomers can trace the growth of supermassive black holes and their impacts on galaxy formation over cosmic time. For example, the discovery of quasars, extremely luminous objects powered by actively accreting black holes, provides a glimpse into the state of the universe when it was only a few 100 million years old. Quasars are thought to represent an early phase of black hole growth, when they were rapidly accreting matter and influencing their host galaxies in significant ways. The feedback from supermassive black holes can also have long-term effects on the structure of galaxies. The energy and momentum imparted by black hole-driven outflows can alter the distribution of gas within the galaxy, leading to changes in its morphology and star formation history. In some cases, this feedback can result in the transformation of spiral galaxies into more elliptical forms, as the central black hole influences the overall dynamics and structure of the galaxy. Additionally, the interaction between black holes and their host galaxies can shed light on the processes that drive galaxy mergers and interactions. As galaxies collide and merge, their central black holes may also come together, leading to the formation of even larger black holes. These mergers can have significant consequences for the host galaxies, including the redistribution of gas and stars, and the potential triggering of new episodes of star formation. The study of galactic nuclei and their central black holes has also provided insights into the role of black holes in shaping the large-scale structure of the universe. Observations of the distribution and properties of supermassive black holes across different types of galaxies have revealed important patterns and trends. For example, the prevalence of supermassive black holes in the centers of massive galaxies suggests that these objects play a crucial role in the formation and growth of large-scale cosmic structures. The connection between black holes and galaxy evolution is further highlighted by the discovery of active galactic nuclei. AGNs are characterized by their intense emission across the electromagnetic spectrum, driven by the accretion of matter onto a central black hole. The study of AGNs provides valuable information about the physical processes occurring in the vicinity of supermassive black holes and their impact on the host galaxy. By examining the variability, spectral properties, and spatial distribution of AGNs, astronomers can gain insights into the interplay between black holes and their host galaxies. Despite the significant advances in our understanding of the relationship between black holes and galaxy evolution, many questions remain. How do supermassive black holes influence the formation and growth of different types of galaxies? What are the mechanisms behind the observed correlations between black hole mass and galaxy properties? How do feedback processes vary across different galactic environments? Future observations and research will continue to explore these questions and refine our understanding of the cosmic connection between black holes and galaxy evolution. The development of advanced observational techniques, such as next-generation telescopes and high-resolution imaging, will enhance our ability to study these complex systems and uncover new insights into the role of black holes in shaping the universe. The interplay between black holes and galaxy evolution is a dynamic and evolving field of study, offering a deeper understanding of the universe's formation and growth. As we continue to investigate the mysteries of supermassive black holes and their impacts on their host galaxies, we gain a greater appreciation for the intricate and interconnected nature of the cosmos. The study of black holes and their role in galactic evolution not only illuminates the past, but also provides a roadmap for understanding the future of the universe. The mysterious lives of stellar black holes, from formation to destruction. Stellar black holes are among the most intriguing and fundamental types of black holes, forming from the collapse of massive stars and playing a crucial role in the cosmic landscape. Their life cycle, from birth to potential destruction, reveals much about the processes that govern the evolution of stars and the dynamic nature of the universe. Understanding stellar black holes offers insights into the broader mechanics of black hole formation, growth, and the ultimate fate of these cosmic entities. The story of a stellar black hole begins with the death of a massive star. Stars are born from clouds of gas and dust in space, undergoing nuclear fusion in their cores to produce energy. This fusion process creates a balance between the inward pull of gravity and the outward pressure of radiation. However, when a massive star exhausts its nuclear fuel, this equilibrium is disrupted. Without the support of radiation pressure, the core collapses under the force of gravity, leading to the formation of a black hole if the mass of the core is sufficient. The formation of a stellar black hole typically occurs in one of two ways. In the first scenario, a massive star undergoes a supernova explosion, a violent event in which the outer layers of the star are expelled into space, while the core collapses into a black hole. This explosion can be accompanied by the creation of a neutron star if the core mass is not high enough to form a black hole. In the second scenario, a black hole can form through the direct collapse of the core without a supernova explosion, particularly in the case of very massive stars. Once formed, stellar black holes can vary in mass, depending on the initial mass of the progenitor star. Stellar black holes typically range from about 3 to 20 times the mass of the Sun, though some can be more massive. These black holes are often detected through their interactions with companion stars or their effects on surrounding matter. For instance, in a binary system, a stellar black hole can pull material from its companion star, forming an accretion disk and emitting X-rays that can be observed with telescopes. The life cycle of a stellar black hole involves more than just its formation. Over time, a stellar black hole can continue to grow by accreting matter from its surroundings. If it resides in a binary system, it can siphon material from its companion star, which can lead to the creation of an accretion disk. This disk, heated to extreme temperatures due to friction, emits X-rays and other radiation, making the black hole detectable. In some cases, these black holes can become very luminous and are referred to as X-ray binaries. Another significant aspect of stellar black holes is their potential to merge with other black holes. When two stellar black holes in a binary system orbit each other, they can gradually spiral inward due to the emission of gravitational waves. This process, described by Einstein's theory of general relativity, can eventually lead to a black hole merger. Such events are among the most energetic phenomena in the universe and produce gravitational waves that ripple through space-time. The detection of these waves, first observed by the LIGO Observatory in 2015, has opened a new avenue for studying black hole mergers and their effects on the universe. The eventual fate of a stellar black hole depends on various factors, including its environment and interactions with other objects. In some cases, a stellar black hole may continue to accumulate mass and eventually become a more massive black hole. In other scenarios, it may be involved in dynamic interactions, such as stellar encounters or mergers, that can influence its evolution. The study of these interactions provides valuable insights into the behavior of black holes and their role in the broader cosmic context. One of the intriguing aspects of stellar black holes is their potential to impact their host galaxies and the formation of new stars. The energy and matter ejected during a black hole's accretion process can influence the surrounding gas and dust, potentially triggering new episodes of star formation. This feedback mechanism highlights the interconnected nature of black holes and their environments, showing how they can both influence and be influenced by the processes occurring in their vicinity. The study of stellar black holes also involves examining their role in the broader cosmic evolution. Stellar black holes are thought to be the progenitors of the supermassive black holes found at the centers of galaxies. Understanding the formation and growth of stellar black holes provides crucial clues about the processes that lead to the creation of supermassive black holes and their impact on galaxy evolution. The transition from stellar to supermassive black holes is a key area of research, as it helps to bridge the gap between different types of black holes and their respective roles in the universe. Despite significant advancements in our understanding of stellar black holes, many questions remain. How do different environments and interactions influence the growth and evolution of stellar black holes? What are the mechanisms behind black hole mergers? And how do they impact the universe? How do stellar black holes contribute to the formation and evolution of supermassive black holes? Future research and observations will continue to explore these questions and provide deeper insights into the lives of stellar black holes. The development of advanced observational techniques and gravitational wave detectors will enhance our ability to study black holes and their interactions, offering new perspectives on their role in the cosmos. The mysterious lives of stellar black holes, from their formation to their ultimate fate, reveal much about the dynamic and evolving nature of the universe. As we continue to investigate these enigmatic objects, we gain a greater appreciation for the complex processes that govern their behavior and their impact on the broader cosmic landscape. Stellar black holes are not only fundamental to our understanding of black hole physics, but also integral to the ongoing exploration of the universe's formation and evolution. Black holes and the quest for a unified theory, theoretical implications, and future research. The study of black holes not only challenges our understanding of the universe, but also serves as a crucial testing ground for fundamental theories in physics. Black holes, with their extreme conditions of gravity and density, provide a unique opportunity to explore the limits of our current theories and to search for a unified theory that combines general relativity with quantum mechanics. This quest for a unified theory represents one of the most significant endeavors in modern theoretical physics and has profound implications for our understanding of the universe. At the heart of the challenge is the apparent incompatibility between general relativity and quantum mechanics. General relativity, formulated by Albert Einstein, describes the gravitational force as the curvature of spacetime caused by mass and energy. This theory has been remarkably successful in explaining large-scale phenomena, such as the motion of planets and the behavior of black holes. However, it does not account for the principles of quantum mechanics, which govern the behavior of particles at the smallest scales. Quantum mechanics, on the other hand, describes the behavior of particles at the quantum level, where phenomena such as superposition and entanglement are prevalent. Quantum theory has been highly successful in explaining the interactions of particles and the fundamental forces. But it does not incorporate the effects of gravity. This disparity has led to the search for a theory of quantum gravity, which would unify these two frameworks into a single, coherent theory. Black holes play a central role in this quest because they represent the intersection of extreme gravity and quantum effects. The singularity at the heart of a black hole, where density becomes infinite, poses a significant challenge for both general relativity and quantum mechanics. In this region, the known laws of physics break down, and a theory of quantum gravity is needed to provide a complete description of the conditions. One of the leading approaches to developing a unified theory is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but rather one-dimensional strings. According to string theory, these strings vibrate at different frequencies, giving rise to the various particles and forces we observe. String theory has the potential to incorporate both quantum mechanics and general relativity into a single framework, offering a possible solution to the problem of black hole singularities. Another promising approach is loop quantum gravity, which seeks to quantize spacetime itself. Instead of treating spacetime as a continuous entity, loop quantum gravity posits that spacetime is composed of discrete, quantized units. This approach aims to provide a consistent description of black hole singularities and the structure of spacetime at the quantum level. Theoretical work on black holes has also led to the development of the holographic principle, which suggests that all the information contained within a volume of space can be described by the information on its boundary. This principle, inspired by black hole thermodynamics, proposes that the fundamental description of the universe may be encoded on a lower dimensional boundary, providing a new perspective on the nature of space and time. The study of black hole entropy and Hawking radiation has further implications for the quest for a unified theory. Stephen Hawking's discovery that black holes emit radiation due to quantum effects near the event horizon has led to the formulation of black hole thermodynamics, which includes laws analogous to those of classical thermodynamics. The concept of black hole entropy, which measures the amount of information contained in a black hole, raises important questions about the nature of information and its preservation in the context of black hole evaporation. The so-called information paradox is a key issue in this context. According to quantum mechanics, information cannot be destroyed, but the evaporation of black holes due to Hawking radiation seems to lead to a loss of information. Resolving this paradox requires a deeper understanding of the interplay between quantum mechanics and general relativity, and has profound implications for our understanding of the fundamental nature of reality. As research continues, future observations and experiments will play a critical role in testing these theoretical models and providing new insights into the nature of black holes and the universe. The development of advanced observational techniques, such as high-resolution imaging and gravitational wave detectors, will enhance our ability to probe the conditions near black holes and to test the predictions of theoretical models. The quest for a unified theory is not only a search for a single, all-encompassing framework, but also an exploration of the deepest questions about the nature of space, time, and gravity. As we strive to reconcile the principles of general relativity with those of quantum mechanics, we gain a greater appreciation for the complexity and interconnectedness of the universe. The study of black holes offers a unique and profound perspective on these fundamental questions and serves as a driving force behind some of the most exciting developments in modern physics. The Event Horizon Telescope and the dawn of black hole imaging. The Event Horizon Telescope represents a groundbreaking advancement in our ability to observe and study black holes, marking a new era in astrophysical research. Prior to the EHT, black holes were largely invisible, detectable only through their effects on nearby matter. The heart's ability to capture images of black holes offers unprecedented insights into these enigmatic objects and provides direct observational evidence of their existence and characteristics. The concept of imaging a black hole might seem like a paradox, given that black holes themselves are defined by their event horizons, the boundary beyond which no light or matter can escape. However, black holes can be observed indirectly through the radiation emitted by the surrounding matter and the accretion disk. The HT is designed to capture this radiation by effectively creating a planet-sized virtual telescope using a technique known as very long baseline interferometry. This technique involves linking together radio telescopes located across the globe, allowing them to function as a single, extremely large telescope. The journey toward capturing the first image of a black hole began with the realization that such an endeavor would require a global network of radio observatories. The HT collaboration, established in 2012, brought together a consortium of over 200 scientists and numerous institutions from around the world. This international collaboration aimed to address the technical challenges associated with black hole imaging, including achieving the necessary resolution and sensitivity to observe the event horizon. One of the key milestones in the development of the AHT was the deployment of a network of radio telescopes at various locations around the Earth. These telescopes were strategically positioned to maximize the angular resolution of the virtual telescope created by the AHT. By synchronizing observations and combining data from these telescopes, the AHT was able to achieve the resolution required to image the event horizon of a black hole. In April 2019, the AHT collaboration unveiled the first ever image of a black hole, capturing the shadow of the supermassive black hole at the center of the galaxy M87. This historic achievement provided a visual confirmation of the existence of black holes and offered a direct observation of the event horizon. The image revealed a bright ring of light surrounding a dark region, consistent with theoretical predictions of how light behaves around a black hole's event horizon. The success of this imaging effort was celebrated as a monumental breakthrough in astrophysics, validating decades of theoretical work and opening new avenues for research. The image of the black hole in M87 provided several important insights into the nature of black holes. It confirmed the presence of a supermassive black hole at the center of the galaxy and allowed scientists to estimate its mass and size. The observed ring of light, known as the shadow, corresponds to the event horizon of the black hole, providing a direct visual representation of this fundamental boundary. The image also offered clues about the structure of the surrounding accretion disk and the dynamics of the material being pulled into the black hole. Following the success of the M87 image, the EHT collaboration has continued to advance its observational capabilities. Efforts are underway to capture images of other black holes, including the one at the center of our own Milky Way galaxy, known as Sagittarius A*. Imaging Sagittarius A* presents additional challenges due to its smaller size and the need for higher resolution. Nevertheless, the EHT team is working to refine their techniques and expand their network of telescopes to achieve this goal. The impact of the EHT extends beyond the immediate achievement of imaging black holes. The collaboration has driven advancements in data analysis techniques, observational strategies, and theoretical models. The high-resolution imaging provided by the EHT has led to improved constraints on black hole models and has tested predictions made by general relativity. The data obtained from the EHT has also inspired new research into the behavior of matter near the event horizon and the dynamics of accretion disks. Looking to the future, the EHT collaboration aims to build upon its initial successes and expand its observational capabilities. Future upgrades to the EHT network will involve incorporating new telescopes and enhancing existing ones to achieve even higher resolution and sensitivity. These advancements will enable more detailed imaging of black holes and their surrounding environments, providing deeper insights into their properties and behaviors. The success of the EHT also highlights the importance of international collaboration and technological innovation in advancing our understanding of the universe. The ability to capture images of black holes is a testament to the collective efforts of scientists, engineers, and institutions working together to achieve a common goal as the HT continues to evolve and expand. It promises to uncover new and exciting discoveries about black holes and their role in the cosmos. The role of black holes in the evolution of the universe. Cosmic architects. Black holes, long regarded as cosmic oddities, are increasingly recognized as fundamental architects of the universe's evolution. Their influence extends far beyond their immediate surroundings, shaping the formation and growth of galaxies, affecting the distribution of matter, and impacting the overall structure of the cosmos. The influence of black holes on galaxy formation and evolution is one of the most significant aspects of their role in the universe. Supermassive black holes, located at the centers of galaxies, are thought to have a profound effect on their host galaxies. The presence of these black holes can regulate the rate of star formation and influence the distribution of matter within the galaxy. This regulation occurs through a process known as feedback, where the energy and material ejected by the black hole's accretion disk can heat the surrounding gas, preventing it from collapsing to form new stars. This feedback mechanism helps to shape the overall structure and evolution of the galaxy. The relationship between black holes and galaxy formation is further exemplified by the observed correlation between the mass of a galaxy's central black hole and various properties of the galaxy. For instance, studies have shown that the mass of the central black hole is tightly correlated with the mass of the galaxy's bulge and the velocity dispersion of its stars. This correlation suggests that the growth of supermassive black holes and their host galaxies are interconnected, with the black holes playing a crucial role in shaping the overall evolution of the galaxy. Black holes also play a significant role in the formation and evolution of large-scale cosmic structures. The gravitational influence of black holes extends beyond their host galaxies, affecting the distribution of matter on larger scales. For example, black holes can influence the dynamics of galaxy clusters and the formation of large-scale filaments and voids in the cosmic web. Their gravitational pull can affect the motion of galaxies within clusters and contribute to the overall distribution of matter in the universe. The study of cosmic reionization provides further insights into the role of black holes in the evolution of the universe. Cosmic reionization refers to the process by which the universe transitioned from a state of neutral hydrogen to a state of ionized hydrogen, which occurred approximately 500 to 1,000 million years after the Big Bang. This process was likely driven by the radiation emitted by the first generations of stars and black holes. Understanding the role of black holes in reionization helps to shed light on the early phases of cosmic evolution and the formation of the first galaxies. The impacts of black holes on the universe is not limited to their immediate surroundings. Black hole mergers, which result from the collision of two black holes, produce gravitational waves that ripple through spacetime. The detection of these waves, first observed by the LIGO Observatory in 2015, has opened a new avenue for studying the effects of black hole mergers on the universe. Gravitational waves provide valuable information about the properties of black holes, their interactions, and the overall dynamics of the cosmos. The formation of black holes and their subsequent evolution also play a role in the distribution of heavy elements throughout the universe. When black holes merge or undergo accretion events, they can produce and eject heavy elements into the surrounding space. These elements contribute to the chemical enrichment of the interstellar medium and the formation of new stars and planetary systems. Understanding the role of black holes in this process helps to elucidate the origins of the elements that make up stars, planets, and life itself. The study of black holes also provides insights into the nature of dark matter and dark energy, two of the most enigmatic components of the universe. Although black holes themselves are not directly associated with dark matter or dark energy, their gravitational effects can help to probe the properties of these mysterious substances. For example, the distribution of black holes in galaxy clusters can provide clues about the presence and behavior of dark matter, while the expansion of the universe influenced by dark energy can affect the growth and distribution of black holes. The future of black hole research promises to yield even deeper insights into their role as cosmic architects. Advances in observational techniques, such as the development of next-generation telescopes and gravitational wave detectors, will enhance our ability to study black holes and their impacts on the universe. These advancements will provide new perspectives on the formation and evolution of black holes, their interactions with their surroundings, and their contributions to the overall structure of the cosmos. The quest for understanding the event horizon, what lies beyond. The event horizon of a black hole is one of the most intriguing and mysterious features in astrophysics, often described as the point of no return. It marks the boundary beyond which no information or matter can escape the gravitational pull of the black hole, making it an enigmatic and inaccessible region of space. The quest to understand the event horizon and what lies beyond it has driven significant advancements in both theoretical and observational physics. The event horizon is defined as the surface of a black hole, beyond which the escape velocity exceeds the speed of light. This means that any object or radiation crossing this boundary is inevitably drawn into the black hole, making it impossible to observe or retrieve information from within. The event horizon is a critical feature in the study of black holes because it delineates the region where gravitational forces become so intense that they overwhelm all other forces, including electromagnetic forces. One of the key theoretical challenges associated with the event horizon is understanding the behavior of matter and information as it approaches this boundary. According to general relativity, the event horizon is a smooth, mathematical surface that forms a boundary between the observable universe and the singularity at the black hole's core. However, this smooth description is complicated by quantum effects and the need to reconcile general relativity with quantum mechanics. The information paradox is one of the most significant issues related to the event horizon. This paradox arises from the apparent contradiction between the predictions of quantum mechanics and the nature of black hole evaporation, as described by Stephen Hawking's theory of Hawking radiation. According to quantum mechanics, information about the state of a physical system cannot be destroyed, but Hawking radiation suggests that information falling into a black hole might be lost when the black hole evaporates. This has led to a debate about whether information is truly lost or if it can be recovered in some form. Various theoretical approaches have been proposed to address the information paradox and the nature of the event horizon. One such approach is the holographic principle, which posits that the information about a three-dimensional region of space can be encoded on its two-dimensional boundary. In this view, the information falling into a black hole might be stored on the event horizon itself, providing a way to preserve information despite the black hole's gravitational effects. Another important concept related to the event horizon is the firewall hypothesis, which suggests that a high-energy firewall might exist at the event horizon, incinerating anything that attempts to cross it. This hypothesis challenges the idea of a smooth event horizon and suggests that the event horizon could be a highly energetic and chaotic region. The firewall hypothesis is controversial and has sparked considerable debate within the scientific community, as it raises fundamental questions about the nature of space-time and the behavior of matter near black holes. The study of the event horizon also involves investigating the black hole interior and the nature of the singularity at the core. The singularity is a point of infinite density and curvature, where the known laws of physics break down. Understanding what happens at the singularity and whether a complete theory of quantum gravity can provide a consistent description of this region remains one of the major challenges in theoretical physics. Observational efforts to probe the event horizon have made significant progress with the advent of the Event Horizon Telescope. The HT's imaging of the black hole in M87 provided a direct view of the event horizon's shadow, offering valuable information about the size and shape of the event horizon. While the EHT cannot directly observe the interior of the event horizon, it provides crucial insights into the behavior of matter near this boundary and helps to test theoretical predictions. Future advancements in observational techniques and theoretical models will continue to enhance our understanding of the event horizon. Upcoming projects, such as the Next Generation Event Horizon Telescope, aim to achieve even higher resolution imaging and to study additional black holes, including Sagittarius A** at the center of the Milky Way. These efforts will provide more detailed views of the event horizon and contribute to resolving key questions about the nature of black holes.